So good morning. I just wanted to make sure that everybody is being able to work on homework 3, which was originally due today, but we'll accept submissions today and on Tuesday in class at the start of the lecture. So it gives you some extra time. So if you see here, there are 4 problems. Problem 17.11. If you see the textbook, problem 17.11 involves data that at the outset looks like it's nonlinear. You are being suggested to fit it to a template or a function that looks like this: y equal to alpha times x multiplied by exponent of beta x. So you need to linearize. How many of you got that you need to linearize? Good. And you linearize it. I think we went through this example in class. So you just divide both sides by x. This is equal to alpha times exponent of beta x. And then you take the log of both sides. So ln of y over x when plotted against x will give you, when plotted against, my apologies, when plotted against ln of x, ln of y over x when plotted against x will give you linear data which you can fit to figure out what alpha and beta are. And actually this was something we did in class. So if you see here, problem 17.11. So this is practically a giveaway. If you mention, if you didn't have this on your homework, yeah, it's going to be hard. But we also did, if you see the next problem in the homework, problem 17.20. Now it says using least squares regression, which you can do by linearization, or you can also do it the hard way, which is to actually apply Newton-Raphson and solve for alpha and beta. I'm giving you a third option. You can just go to MATLAB, solve problem 17.20. Oh, sorry, hold on. This is not that problem. 17.20 is this. Use nonlinear regression to fit a parabola or a second order curve to this data. So you are asked to fit for y equal to, say, a0 plus a1x plus a2x squared. This is the type of curve you need to fit, which you can fit using least square regression. So you need to set up 3 equations with 3 unknowns to solve for a0, a1 and a2. Were you able to try that or do that? Right? This is also similar to an example that we did in class. I think we might have done the same example as well. Did we?
No, we did 17.5.
17.5. Okay, so let's see here.
We might have done it
During the recitation session.
So is that one a polynomial?
Yep, it's a second order polynomial that you need to fit. Okay, so you will set up 3 equations in 3 unknowns to get a0, a1 and a2. And then third problem, you are asked to look at problem 18.9. Okay, 18.9, let's just go to that chapter. 18.9. Here's the data. Use Newton's interpolation to determine x equals, determine y at x equals 3.5 using the following data. Okay, you don't have to do Newton's interpolation. That is just a generalization which we didn't go through. We studied first order, second order, and up to even third order interpolation. Thank you. Third order interpolation, which you can use. So it talks about best possible accuracy. You are welcome to pick any order and provide short justification why you pick that. Okay. So say for example, you can choose first and second order and say the difference between them is not much. So first order is good enough. Or you can do first, second, and third and see which of those gets you decent accuracy or comparable accuracy. So don't just ignore this one phrase. Just don't worry about Newton's interpolating polynomial. Just use first, second, or third order interpolation. That's it. Okay. problem 18.28. Same thing. You have been given data and you are asked to estimate the oxygen concentration at a temperature of 27 degrees Celsius using linear interpolation. You can ignore Newton's interpolating polynomial and just do cubic spline, meaning first and third order, and they also give you the exact result. So you can use that to see which or how much accuracy you get with first and third order interpolation. Okay. Now, I know some of you have questions about how to present your submission. Please ask them now. Any questions? Yes. Can you please be louder? Right.
So I know you want like screenshots of the Excel file.
Right.
Is it possible, like if we screenshot it, does it need to be like the actual visual Excel, or could we like screenshot it and put it into like a Word document?
That's fine. You are giving us a paper submission, so it makes no difference to us whether you print it from Excel or Word, as long as it's visible. Yes.
So you want Excel file screenshots along with a handwritten?
Yep, it says right here. We will only grade the handwritten work. The screenshots must be there for us to just have some kind of reference that you did the work on Excel, and then these numbers are based off of some calculation. If you just give us the handwritten numbers without the details, we won't know where these numbers came from. That is why I'm asking for the screenshot, which will not be directly evaluated. So if the screenshots aren't there, your solution will look more tenuous. If the screenshots are there and the solutions are correct, you are likely to get a high score. That's the logic. Other doubts about how to prepare your submission? So if there aren't any, we will accept the submissions at the start of lecture next time on Tuesday. Okay, so you're getting that few extra days. So coming back to the world of differentiation. So we were discussing numerical differentiation. Can I get some simple common language summary of what this process is? If I give you a table of data, X and Y, X1, Y1, X2, Y2, X3, Y3, and so on. We saw what is interpolation. We saw what is regression. And now to the same table of data, you're doing another operation called differentiation. Can somebody tell me what exactly are we doing here in simple words? What is differentiation? You have functions whose analytic form is known. Differentiation is just the process of obtaining derivatives of the first order, second order, third order, which all have some physical implications. So what is the most common interpretation of the first derivative? Velocity fits time domain. So we will think f dash of t represents dy over dt, which is speed or velocity. And if it's in the spatial context, usually this is referred to as slope, right? And the second derivative, acceleration, thank you. Acceleration, concavity, or more generally speaking, curvature. curvature. I don't know if third and higher order derivatives have any specialized names, but we are all very familiar with slope, curvature, speed, and acceleration. The whole reason we do this exercise is that most often real life doesn't produce functions, it produces data. And when we get data, it is in a tabular form. It has a independent variable which is varied, like for example, it could be a spatial coordinate or it could be time, and a dependent variable which is measured as a function of the independent variable. So you measure the location as a function of time, or coordinate as a function of time, or you measure some quantity y at different points in space. So if you have a bar, and if you record the temperature at each point, what is this quantity? What is the name you give to this quantity in heat transfer? The rate of change of temperature along the x direction, what do you call it by? Sorry?
Could you call it thermal gradient?
Thermal gradient or temperature gradient. Thermal gradient, and the word gradient is nothing but it's like saying something is changing with space. So whatever that something is, you get that gradient. So the most common applications of this numerical differentiation is to take measurements as a function of space or some spatial coordinate and use numerical techniques that we learn to compute the gradient, which is often important in the analysis of the problem. Okay. So last lecture we learned how to calculate approximations of dy over dx or d squared y over dx squared, or construct any derivative in terms of, for example, if you are interested in the derivative at a point, we'll call it say xi, in terms of its nearest neighbors as well as neighbors once removed, twice removed, thrice removed, and so on. Okay. So we approximated dy by dx as three ways. Can you recall what those three ways were? If I take the current point and use the current point and the next point to compute my derivative, what was it called? Forward derivative. So forward derivative is like writing yi plus 1 minus yi divided by delta x. This is forward. And same logic, if I use xi and my neighbor behind me, what that would be called backward. Yi minus yi minus 1, that was backward. If I use neighbors both in front of and behind me and write the expression, that is called central difference. Thank you. Forward, backward, central. Are we together so far? We saw all this last time. Just a recap. When you think about this derivative, which may come from the actual mathematical operation of differentiation, to this derivative which you get by numerically approximating it, what is the difference between this and this? What is the difference between what you get? Suppose y equal to x squared, then you know that dy by dx is equal to 2 times x, and if you want it at any particular point, you would write dy by dx at I equals 2 times xi. It's very easy to do this. You have been doing it for a long time. What is the difference between doing it this way and doing it this way in terms of how much error do you pick up when you do this kind of approximation? So this is sort of important that you keep track of, because everything comes at a cost. your approximation of the derivative also comes with a cost in terms of accuracy. So this is just a big recap because we had the fall break in between, and I think some of you might have not might not recall this. So we start with Taylor series. You need to remember this, write it down, bring it to your exam, okay? Somehow this is the starting point for all the approximations we'll derive. The y value at I plus 1 is equal to the y value at I plus the slope multiplied by delta x plus the second derivative multiplied by delta x squared over 2 factorial plus and so on up to infinity. This is the starting point for all derivations of approximations to these derivatives, okay? So then what we did was to say yi plus 1 minus yi divided by delta x, this is equal to dy by dx at I plus d squared y by dx squared at I multiplied by delta x over 2 factorial plus and so on up to infinity. Until now, there is an equality sign because we haven't thrown away anything. It's all exact on both sides, both the left side and the right side. Now, we will discard this term or discard this sum, which now becomes the error associated with approximating the derivative using finite number of y values, which could involve I plus minus 1, I plus minus 2, and so on. It could involve yourself, first neighbor, second neighbors, third neighbors, and so on both sides. We saw this also. So then we write dy over dx or dy by dx at I is approximately equal to yi plus 1 minus yi divided by delta x, and the error associated with it scales as what? What is the leading power of delta x in this summation that you discard?
The n.
It scales as delta x to the power 1. Okay. So this is the procedure to get a approximation for this is first derivative. What kind of differencing is this? I plus 1 and I. Forward differencing. And what is the order of magnitude of the error?
1.
So it is first order in accuracy. The very subtle point. You are all most of you are all native English speakers. I'm not. This is first derivative, first space derivative. This is first order accuracy with a hyphen. So this order refers to the accuracy, and what we are saying here is this is when you start your process, you decide these a priori. Yeah, you want the approximation of a first derivative or a fourth derivative or a sixth derivative, whatever. And you decide I will do forward or backward differencing, which is usually governed by the physics of the situation. The accuracy you get here is usually a consequence, it's an outcome. After you do the derivation, only you will know what accuracy you end up with. Okay, so this is usually determined only at the last step. Let me ask the question. The quality of your approximation, does it get better as you make delta x smaller, or does it get worse as you make delta x smaller? You have a table of data, let's say, and you want to evaluate the derivative at any particular point. Say you want to get dy by dx at x2. If x1, x2, x3, if the data is finely spaced, would your accuracy be better, or would it be better if it is coarsely spaced?
It's finely spaced,
Because
because if it's coarsely spaced, it won't be as nice, I guess.
so you can just say delta x, say for example, whatever we consider as coarsely spaced is in steps of 0.5. So you have, for example, 0, 0.5, 0, 1.0, 1.5, and so on. And whatever we call fine, let's say that has step length of 0.05. So obviously the magnitude of the term you throw away is bigger because delta x in the first case is 10 times bigger. So it's always good practice to choose step lengths that are the finest you can possibly choose. Okay, so we'll do a numerical example now, and we'll try to use a coarse and a fine step length for you to compute the same quantity at the same point, but with different resolutions. That makes sense what we're trying to do? Same point, same quantity, but with two different resolutions, and you will see the difference. Okay. Give me 1 second. All right, good. Okay, so I just created two sets of data, x and y, where say for example in the first table the step length is 0.5, that is the x values change in steps of 0.5. Okay, and in the second table the x values change in steps of 0.05. Okay, we'll pick any one particular point. Let's say, for example, we pick this case, or we pick this value x equals 3. The y values are given to you. So you have the current, you have the first neighbor forward, first neighbor backward, second neighbor forward, second neighbor backward, and so on. And if you scroll through this table, the second table, the at x equals 3, we have the value 14. Okay. Wait, did I get this functions right? Oh, okay. Plus 1. No. Plus 1 minus exponent. G4 squared plus 1. All right, so at x equals 3, I have 14 here, and why do I have 13 here? All right, I have the same thing here. Good. So I'm going to choose these values. Okay. At x equals 3, I have my immediate neighbors. You don't have to create the entire table. You just need 3 values for the moment. I want you to calculate the value of the first derivative using a central difference approximation at x equals 3, using the first set of data and then the second set of data. We'll also do this for second, third order derivatives, and there is a point to make there. Okay. So start with the first derivative. Start with the first derivative. So here the step length is delta x equal to 0.5. Okay. You want to compute dy by dx at I, and the formula is, what is the formula? It involves the first neighbor. So this is I plus 1, and I minus 1. So the formula is, so if you are in the exam and you forget the formula, what is your starting point? Always this equation. Always this equation. And how do I get central differencing here? I need to consider yi minus 1 is yi minus dy over dx at I multiplied by delta x plus d squared y over dx squared at I multiplied by delta x squared over 2 factorial plus and so on. So then if I add these two lines, I'm going to get dy by dx is yi plus 1 no, I'm going to subtract this time, not add, because I want to get the first derivative. So this is yi plus 1 minus yi minus 1 divided by 2 delta x, and the order of magnitude of the error would be what? If I subtract these two rows, this goes away, doesn't it? Because these have the same sign, same magnitude, and you'll have a third term, d cube y over dx cube at I, delta x cube over 3 factorial plus and so on up to infinity, and then I have minus d cube y over dx cube at I, delta x cube over 3 factorial up to infinity. So you tell me, what is the order of magnitude of my error? This term, these two equations I'm subtracting, so it will be 2 times d cube y over dx cube at I multiplied by delta x cube divided by 3 factorial. But when I rearrange, I also divide by delta x. So what will be the order of magnitude of my error? Second, right? So this term, you're going to lose a delta x and you're going to get delta x squared. So the terms that you throw away, which are starting from here, they have an order of magnitude delta x squared. That makes sense to you? No? Yes? No? Okay. So can you tell me which one doesn't make sense? All of it?
Yeah.
Okay. So from which step should I kind of come back? So let me try this. I'm going to spend just a little bit of time going through this again, little slowly. So you are here. This is point I. In our case, what is the value of xi? 3. And then the next point is xi plus 1, which is 3.50. And the previous point is xi minus 1, 3.25. I'm sorry, 2.75. I'm sorry, 2.50. Okay. So if you are here, suppose the function has a value yi here, and it has a value yi plus 1 and yi minus 1. That's what this 9.75 is, and 16.75 and 13.00 is. Do we all agree that these 6 values are known to us? Using that, we want to construct an approximation for asking what is the slope at this point. We want to know what is dy by dx at I. This is our goal. Okay. The starting point for that is always Taylor series. That is, Taylor series talks about if you know the value at a point, how do you construct the value at an adjacent point? That's the core concept behind Taylor series. And it is written as the value at the adjacent point is equal to the value at the next point plus first order corrections plus second order correction. That is, you're correcting for, if you go from here to here, it depends on what is the local slope, and it also depends on what is the local curvature and the local third order derivative, fourth order derivative, and so on. Does this make sense to you? So you have first order correction, second order correction, third order, and so on. You can think about infinite order correction. That is, there are infinite derivatives that you can keep on computing. Because you don't know what the function is. If your function was a second order polynomial, you would jump up and say, beyond third derivative, there is nothing to compute because all the derivatives from there on is just 0. But numerical differentiation is by definition what you do when you don't know the function. So you have all these corrections in principle. So this is written as yi plus dy by dx at I multiplied by delta x plus d squared y by dx squared at I multiplied by delta x squared over 2 factorial and so on up to infinity. How do I know this? I memorized it. And you should too. Unless you want to actually spend a lot of time learning the roots of Taylor series. You're with me so far? So now I want to know not only the next point, I also want to involve the previous point. And the previous point is nothing but this is xi, this is xi plus delta x, and this is xi minus delta x. This is backward, so step is negative, taking a backward step. So that would be yi minus 1, that is the value of the function at this point, is the value of the function at this point, yi, minus dy by dx at I times delta x. Replace delta x with minus delta x wherever it appears. That's the simple strategy. And the next term, d squared y over dx squared at the point I multiplied by negative delta x the whole squared divided by 2 factorial and so on up to infinity. Again, none of this is new. We did all this. I'm just trying to reinforce. Now, your goal is, keep remembering your goals, is to get dy by dx at the point I. What will you do to get that? I will pose the question to you. What will you do to get dy by dx at I, given you have involved the forward neighbor and the backward neighbor? You want to say something?
You isolate dy dx at I and subtract the thing.
Or to put it more generally, you do whatever is needed to isolate the term that you are after and rearrange the terms, remaining terms. So if I do that, I'm going to skip a step. That is, in the sense, I'm going to skip the algebra and just write dy by dx at I equal to yi plus 1 minus yi divided by 2 delta x plus, when I subtract, this term just cancels away. So the next term will be d cube y over dx cube at I multiplied by delta x cube over 3 factorial, and I have to multiply it by 2 because there will be 1 in this row and 1 in this row, which will add up to give you that factor of 2. So it's like saying your derivative that you want to get is this term. Can you tell me, can this term be computed with the information provided? You know y at the next point, you know y at the previous point, you know the step length. So none of this is going to be a surprise for you. So this can be computed, whereas this cannot be computed. Why? Anything from here on cannot be computed, because you don't know what the third derivative is. You are trying to calculate the first derivative. How would you know the third and fourth and so on? So all of this is bundled into one term called error, and we say, okay, actually this should be 1 over delta x times this infinite series, and the error has a order of magnitude. So this goes as delta x cube and you divide it by delta x. So the error scales as delta x squared. So if your delta x squared is high, your error will be high. If your delta x squared is low, your error will be low. That's the implication. It grows with the magnitude of delta x. Okay. So you want to take this formula now and use it with that data. So use this formula with these 3 points and tell me what is the value of the derivative at x equals 3.00. Go ahead, do that. So if I take the next point, that is 16.75 minus previous point divided by 2 times the step length, which is 0.5, I get 6.999, or I'll just say, if I round it to 4 decimal points, 7.0000. This is the slope at x equals 3.00. 1 second. Okay. Yes.
For the equation we use I minus one as, y I, right?
Yeah, this is I. This is I minus 1. This is I plus 1. Next, current, previous. Or if you want to use forward, current, backward. Yes.
And what was the function that's in the problem?
That I think about this as simulated data. You don't know what that function is. You don't need to know. All you need is the data which is given. I made up that function. Is it making better sense now? Thank you. Yeah.
Let's see the function that you use for f.
You don't need to. You will not be able to in real life. You just copy these values. Okay. So if I turn this column into 4 decimal points, you just copy the value that is on your screen and work with it. So these are the bold, the values in bold is what you need to do this calculation. Yes.
So what you put in a box at the bottom, you can put y I plus 1 minus y I minus 1.
Yeah, this is a error I made just now. Good. Yeah.
So when you do the above, like what's in the box, they alternate signs because like only the odd powers alternate signs.
Only odd powers alternate signs because wherever you have delta x, you replace it with negative delta x. The even powers don't change because you're squaring it or raising to the 4th or 6th or 8th power. Okay, these kind of quirks will happen, and that's why when I said the order of the error or accuracy cannot be known a priori, that is precisely due to these quirks. Sometimes these things cancel out and give you more accuracy than you initially thought. Okay, we are going to do a few more operations with this data, so we are not done yet. Is everybody able to get the slope at x equals 3 with these 3 data points? Right? Okay. So now this data set was with a step length or step of 0.5, and this one is with a step of 0.05, and I'm going to take all of this, move over to where x equals 3 is. Okay, and I have more fine resolution data where I have 2.95 and 3.05 instead of 2.5 and 3.5, and I have these y values. So now I want you to write slope at x equals 3.00 with the formula, y I plus 1 minus y I minus 1 divided by 2 times delta x. Did I put the 2 back there? Yep. Okay. So what would you do? You take the next minus the previous divided by 2 times 0.05. Put it in there. That is, you can do it with your calculator. You just need these 6 values. You can write it in your sheet and then do the calculation. So if I hit enter, okay, you get 6.99975, which if I round off to 4 decimal points, I would still be ending up back with 7. At least let's all of us complete the calculation, and then we'll select our, or we'll get a different data set which will tell perhaps the story that I want to tell. Okay. All right. So if you are able to get until this calculation done, take a pause. I'm going to change the data set. I'll take a very simple function, okay? That one that I know will quickly raise to very high values. All right. So I'm changing my data to just write exponent of 4 times x, so that I'll have something that grows pretty quickly. Okay. Or I'll write exponent of x, and this is exponent of . All right. So don't have to write. I'll give you time. Here is the illustration. At x equals 3, okay, I get my value of y to be 20.08, and the slope is around 20.93. Okay, let's go over to the fine resolution data and see what the slope happens to be. 20.09. 20.09 versus 20.93. There's a small difference. So I want to accentuate this. Oops. Oh, this is interesting. All right. Now I have the story I want to tell. So you tell me what's going on. You have x equals 3, 8103, and 3.5 and 2.5. That won't change. If you go to the other data set also, at x equal to 3, you have 8103. So same value of x, you're just selecting a different step length to compute the forward and backward neighbors, and the slope estimate is 24,400. Okay, let me write it down. I'm going to write it here. With a step length of 0.05, the slope dy by dx at x equals 3 is 24,400. And what was it previously? 34,000. That is, with delta x equal to 0.5, the slope is dy by dx at I is 34,500. Now, question for you. Which one do we trust more? Because louder, please. People in the back have to hear. Since we have more data points total, we can get more accurate. So, first reason, I'm rephrasing what you said. When you look at your formula, you know that the error scales as delta x squared. The smaller you make your step length, your error becomes smaller. That is a reason to always prefer smaller step length or higher resolution in your data. Where do you stop? Why do 0.05 and stop there? Why not keep going smaller and smaller and smaller? What's the problem there? Or what is the problem? Or where do you stop basically? Is this better than 0.01? Probably not. 0.01 will give you even better estimate. So where do you stop?
I think we mentioned this last time. You said if it's larger than 1, it'll scale differently than if it's less than 1.
It is going to be less than 1 in most applications. Like, let's say in this discussion it is less than 1. So you have to keep making it smaller. How small do you go? Yes. Do you want to say something?
Well, the smaller you go, the smaller the error is going to be. So would it be a matter of the user indicating their error, like we did in the previous questions?
See, you don't know the error. You know the slope, estimates, let's call them estimates. This is slope estimate 1 and slope estimate 2. You can only compute error if you know what the truth is, which you don't know. I simulated this data. It might as well be in a data set that came to you just as a printout without telling you what that function is. I used some function. You don't know that. You didn't see that. So you can't estimate the true error ever until you know the truth. So where do you start?
Do you just use discretion on depending on what you're doing? Like,
Yes, you use discretion, but based on what?
what you're doing, like, if it's, hey, if you're doing velocity of the car, it probably wouldn't make sense if you're doing like, if you're doing like 0.01 miles an hour, 0.02 miles an hour. I guess just.
So in what you're saying as an engineer, there is a finite limit on resolution with which you can get data. If you have a velocity transducer and you have your speed indicator on your car, it has step size of only say 1 or 5 miles per hour. That's the resolution you can get. Or if it has a digital display, it says 60.0 miles per hour, or it will say 100 miles per hour. Either case, you get only 3 significant figures. You can't get more resolution than that. So your resolution is, if you are less than 100, it's 0.1 miles per hour. If you are more than 100, it's 1 mile per hour. That's your resolution. You can't go better than that. Okay, that is engineering, that is reality. In computational science, that is when you're trying to solve equations of physics using numerical techniques, you can go as much fine in resolution as you want. There is no limit to your resolution. How fine do you go before calling it, this is good enough?
You could take the difference between the two slopes you got
Okay,
and wait until it gets small enough at your own discretion for whatever application you're using. So if it is for a car, if you get less than, I don't know, 0.1 miles an hour, it's not gonna make any more difference for you to get more finer than that for the slope.
right.
So if you're that fine, you will need to make it more accurate.
I completely agree with you. And for those who are listening, I hope you understood what he said. If not, I'm going to rephrase it. He's basically saying you can continue reducing it, but at one point the gain will be marginal or non-existent. So the difference, the slope estimate is 34,500. The slope estimate is 24,400. Let's say we try one more with 0.005 and you get pretty much the same slope. What does that mean? It means there is no gain in going from 0.05 to adding to making it 0.005. You might as well use the coarser one if it gets you the same results. Two products, one of which gives you the same performance at a lower price. What will we naturally prefer? We'll prefer the one which has the lower price. Yes.
Would you want to go like finer and finer until like the difference between, you know, your data sets that you're finding, when that difference is like just below the resolution of your measurement device?
There are two things here. One is resolution of your measurement device or resolution of data collection is a hard limit that is determined by your hardware or the sampling or the actual modus operandi by which you collect data. That has nothing to do with what we are doing here. If you are like in the car example, if you can't get any finer than 0.1 miles per hour, that is it. You have to accept whatever estimates you make at 0.1 miles per hour and live with it. There is no more tweaking you could do. But on the other end, suppose we are still within that hard limit. And for computational work, that is, if your goal is to solve, say for example, an ordinary differential equation or a partial differential equation, you are discretizing a domain, and the number of divisions you can make is practically infinity. You can keep on dividing it in as fine as you like chopping meat. It's basically, even that is a bad example, because how fine can you chop your meat? It depends on the blade's resolution or the thickness with which your blade can slice, right? Fun fact, there is an instrument called cryomicrotome, which I recently learned about, which is used to, so when they do experiments with rats or mice, they euthanize that animal, they freeze it whole, just whole, and then they remove the teeth, and then they just put it through this imaging cryomicrotome, which is like a very fine salami slicer and can slice 10 microns thickness slices. That is, imagine an animal's lung which has some kind of volume. You can slice it in thicknesses of 10 microns. And it is used for research. Anyway, fun fact. But if we are staying within our physical hardware's limits, how do you select which resolution is good? Practically speaking, to wind up the discussion, I would do one more and I'll try to make this estimate. I'll try to plot what is my estimate of the quantity that I'm trying to calculate. So in this case, it's the first order derivative. That estimate at a step length of say 0.5, 0.005, and I'll also do 0.005. And if the gains are flatlining, I can think that these two are practically the same. If there is no more gain, why bother doing more? Want to say something?
So is this like in our problems earlier in the semester where like, let's say between the 0.05 and then the 0.005, you could run like, you could do like an error program that says like, and you have your error margins, and once it falls below that, you can stop doing.
Absolutely. That's a great way to say that. Nice. That's exactly what it is. You keep calculating the relative error between successive resolutions, and you stop when the relative error flatlines or goes to zero. Okay, that's a very nice way of articulating it. Good. So let's do one more. That is, I want you to do the same resolution or same calculation at a lower resolution, and we'll see what comes out and stop there and do the move on. Okay. So let me regenerate the data with a step of 0.005, which if you are doing, you can also simply say, I'm going to take 2.995, 3.000, and 3.005. And what is my function? Exponent of 3x. Exponent of 3x. And my slope value is forward minus backward. Oops. Forward minus backward divided by 2 times my step length. 24,310. Very interesting. So remember, we had, let me clear all this. We had 34,500. And when we had the slope with step of 0.05, it was 24,400 and something. And now we have 24,300 and something. So we are there, almost there. If you look at 24,400 and 24,300, they differ by 100 units over 20,000. That's definitely less than 1%. Right? So you are within 1%. So it's like saying 0.005 and 0.05 gets you the same level of accuracy, whatever that level is. So which would you pick? I would pick 0.05 because it is lesser number of data to hold. So when you're thinking data science, you're also thinking about memory, how many bytes, terabytes that I need to handle. It's always simpler to handle less. So I would pick this because it gives me the same functionality or same estimate. Okay. Yes.
When it comes to doing the work on our own, would there be a correct step that we'd have to use? So say in this, if we ended up using 0.005, would that be incorrect?
blanket rule, standing instruction, whatever choices you make, you have to write a short justification. If you are choosing 0.05, then you have to preempt the question, why not anything lower, and say 0.05 and any other lower choice gets me pretty much the same results, hence I'm using this. That one sentence has to be there.
And in that case, would we still need to do the slope or the step of 0.005 so we can compare
Yeah.
values together?
How will you tell me, how will you make an assertion to me if you are not sure if that assertion is correct? How will you have to do the work in order to find out and then tell me. You can't just tell me, that will be lying. Right? So you have to try it. So if the statement is any step length smaller than 0.05 will not give any additional gain. In order to make that statement, you should have tried at least a step length that is smaller than 0.05, preferably much smaller, so that you can make the statement. See, I don't know if I'm expecting something that your other courses don't generally expect. You are expected to produce an answer in heat transfer, how many watts of power was dissipated or something like that. I'm expecting judgment from you at every turn. And I want you to be able to write sentences based on hard numbers. So don't just give me numbers and then wonder why you lost points. Okay. So, any other questions, remarks? Yes.
Would this be a beneficial thing for us to automate?
You can automate. Yeah. What do you want to automate?
You could automate your choosing your step size.
Yeah, that's you can put in as an algorithm the process that we described in words. Yeah, sure. Now, yes.
What was the name of the mouse slicer?
It's called a microtome, TOME, a cryomicrotome. It basically freezes that mouse solid at minus 80 degrees Celsius. And what I was told, I haven't seen one yet. I just I'm working on a collaborative project with another university, and they have one. They said if you just even approach it within like a centimeter, you could be sliced. So don't go near that. Anyhow, all right, come back. This was an example which I struggled to find, and you remember there were two other functions or two other data sets which we originally tried, which gave you the same answer for slope at this coarse resolution as well as that finer resolution. Why did that resolution never mattered in the first function, but it mattered in the later exponential function? What about the exponential function? And I'll tell you, disclose that the first function was a quadratic. It was pretty much a quadratic equation. So it looked something like this. So the function one that we tried is something like this. Okay, it was 1 plus x squared. The second function we tried was exponent of 3x. Maybe it even climbs even faster. Exponent of 3x. This was the second function. Okay, so for the first function, it's like saying delta x equal to 0.5 and delta x equal to 0.05 gave the same slope. Gave the same slope estimate, which was slope equal to 7 at x equal to 3. In this case, delta x equal to 0.005 and delta x equal to 0.000. Sorry, I keep lagging my writing. So in this case, the slope was 35,500 something. In this case, the slope was 24,400, and in this case, the slope was 24,300, which we sort of thought good enough. It won't change much more, and we said either of these two are acceptable. Why resolution mattered here and why it did not matter here? Yes.
the exponential function has an unlimited amount of derivatives that can be taken from it.
Yes,
And an unlimited amount of times it can be differentiated, meaning that it's the error that you get for the Taylor series is going to compound,
keep building,
right?
Exactly.
Whereas the quadratic has only two derivatives.
finite number of derivatives.
So.
So at one point, there is no further gain to dropping your resolution because the higher derivatives don't matter. They just don't exist. I am telling you that this is exponential, this is quadratic in the backend. When the data set is presented to you as a printout or as a file or as a list, you don't know whether it's an exponential data or the quadratic data. What would you do? Would you, even there are two parts, I'll give you two options. One option is keep dropping the delta x until you see no gain in the estimates, until you see no change in the estimates. Option two, you're given data, you are all experts in regression. I think you are, right? Don't disappoint me. You are all experts in regression. Fit a regression and see which order curve best describes your data. That gives you a sense of whether you are dealing with a polynomial here, or an exponential here, or a trigonometric data here. Whatever data, you can always do a curve fit, right? So what would you do?
Repeat the question.
The question is, you are just presented a table of data. Nobody tells you it's an exponent or polynomial or anything. His explanation was perfect, the perfect explanation to this question. It's just saying the reason why it didn't matter here is because whatever the resolution is, the higher order corrections don't matter here. They matter a lot for the exponent. Done. When you are presented with the data, you don't know whether it's exponent or quadratic. What will you do to get started? Whether you will just do this and think that, yeah, this should be good enough, I'll just move on, or will you go through this? Remember, this takes a lot of time. You have to do this at each resolution, time and effort. Whereas this is less effort, but kind of risky. What will you do? Which path will you choose? Yes,
If it was a test. And we're.
it's not a test, it's life.
Oh,
Think about what will you do when you are practicing your art or your profession.
I'd probably just do the spreadsheet for it.
You'll probably do what?
I'd probably just use the spreadsheet for it. 'Cause it's
Use spreadsheet to do what?
well, you can just make a graph and then get it to automatically give you a function for it.
So you will fit a regression.
Yeah.
And
And then you can use that to find the one data that you're interested in.
see, you're just telling about the software. You can do this with any software, but what will you do? So you can do the regression, and the regression will sort of tell you what is the relationship between y and x approximately. And using that as a guidance, you get a sense whether you fall in this kind of paradigm or you fall in this kind of template. That gives you a sense or anticipation about whether you need to do the drill or you can get away with something easier. Okay, you have to exercise some intuition in sensing whether you are dealing with quadratic data or polynomial data or any other kind of data which may be more. So polynomial data is by far the easiest. It's easiest to handle and think about, but not so much exponentials or there is no reason that it should just be a simple exponential. It could be an exponent that is also having a trigonometric component. So there is no guarantee that your data will be nice and well behaved like our examples. Okay, yes.
To test and see if it would be a polynomial, which is something else, you could use a few points to make a regression. And then you could use that same function you've made and test it at a much further point. later on in your table.
Sure.
If it is a polynomial, it will be somewhat near your values, and that way you can use a simpler step. If it's very off, then it's probably going to be something else.
That's a nice way of doing it. You try to make a trend out of, say, the first few data points and see if that trend holds on forever. If it literally holds on forever, then it means linear data. If it sort of holds on, it's probably quadratic. If it doesn't hold on much at all, it's either a higher order polynomial or it must be some kind of function. What is the core of all this? You need to have intuition about functions, graphing them, and how they behave. Without that, if you just have a blank mind, show up and just look at a table of data, you'd be kind of stuck at every point. So that intuition comes from, what did you say? Practice. Thank you. It comes from practice. So the more problems you try, you'll get better. Okay. All right, good. So now I want you to use the same data. Let's stick to this 0.05 set. Okay. And let's try to compute, say, a second order derivative using central difference. To do that, first you need to know, or you need to have a formula ready. I want you to compute d squared y over dx squared at xi equal to 3.00 with resolution delta x equal to 0.05. So first step is for you to have a formula. And you don't have to derive all the formulas. The textbook has a table that lists all these formulas. So why don't we, now that we know the principle, why don't we start using the textbook? I know it's in chapter 19, I think. Give me a second. Yeah, I think, let's see here, regression. Yeah, chapter 23. Chapter 23, if you see figure 23.1, most of the formulas you will need in this course are tabulated for you. First derivative. So look at the first line and tell me what kind of a derivative. It is forward or backward difference. Everybody will say that this is forward, right? No one has any other answer they want to give. I plus 1 and I, forward minus current. Okay. This is the first derivative which involves two neighbors. Is this a forward or a backward or a central difference? Did I hear forward? Yes. Why forward? Because it involves I plus 2, I plus 1, and not anything behind. Second derivative, we have, I should, so simultaneously also pay attention to the order of the error. So second derivative, if you involve only the I plus 2, I plus 1, that is involve two neighbors, you get an error of h. If you involve three neighbors, you get h squared. Okay, so which is higher accuracy here? Which gets you higher accuracy? Formula line 3 or line 4? Line 4. Line 4, and because the error scales with h squared, so as h is a small number, h squared will be smaller. So the error will be smaller with line 4. So all these the entries in this figure, they are all forward derivative or forward approximations. So that's given at the top right here. So if you scroll further, figure 23.2, backward formulas, and then central formulas. Okay. So the exam scenario is, if you have your textbook with you, which I'll allow, I am okay with that. You bring your textbook and you're asked to compute, let's say, for example, the third derivative to using a backward difference formula. You need to know which table to look. You pick out that formula The last thing you want to do in the exam is write out the Taylor series and derive everything from scratch, which is not a good use of your time. Okay, so you should know these tables. So just for practice, why don't you pick out the second derivative formula using let's see here, using forward and using three neighbors, that is forward and using three neighbors. I don't know, how should I say that? Third order, but that will be confusing because the error is of the order of h squared. Let's say you pick out this formula and compute the second derivative for the data set that I have. So I'll give you a minute to write down this formula on your notebook or your Excel sheet, and then I'll switch to my data.
Here's delta x, right?
H is delta x, correct. Sorry, I didn't mention that. H is I use delta x, they use H. That's the only difference.
What page is this in text?
This is
No.
656.
Does it matter if we use the center backward or forward one?
I'm going to make you do all three. All three, but that involves higher order neighbors. This is just like two neighbors, this is three neighbors. So this is just like net practice. You have to kind of, what you guys call it, cage practice. You're doing softball or baseball. So write down the formula. Okay, maybe I'll take a screen like a screen capture and paste it into my Excel sheet. Okay, so I'm going to paste it here. Oops. Yeah, so here is my formula. Okay, and I'm still focused on my, actually let me duplicate this sheet because later I want to post this. Okay, so I don't want all my slope values in delta x equal to 0.5. That is all ancient history now. I'm just going to keep this table. So let me move over here. So I want to get the slope, or this not the slope. This time we are getting the curvature. Curvature at x equal to 3.00. I involve current, that is I plus 1, I plus 2, I plus 3. I don't involve anything behind at the moment, so let me not highlight it. And these are the values I'm going to use. So what do? You punch in this formula into this cell, or in your paper, you can just use these values and get me the value of the curvature using a forward difference approximation. So this is minus the value at I plus 3 plus 4 times the value at I plus 2 minus 5 times the value at I plus 1 plus 2 times the value at I divided by h squared, h being 0.05 squared. This is curvature, second derivative. So this is curvature. Okay. And this value is this value is forward differencing involving three neighbors. I want you to do again backward differencing involving three neighbors. That is, pick out the formula with which you can get the same quantity, but in backward differencing method, which involves three neighbors. So those neighbors would be I minus 1, I minus 2, and I minus 3. So this will be backward. And this will be forward. Backward differencing involving three neighbors. First, pick out the formula. Sorry for my rush, it's almost time, that's why. So pick out the formula, which if you go to, okay, actually let me add here, this formula came from table 23.1 or figure 23.1. Okay. So if I go to figure 23.2, here is my formula. So this came from figure 23.2. Oops. 0.2. So that will be 2 times the value at I minus 5 times the value at I minus 1 plus 4 times the value at I minus 2 minus the value at I minus 3 divided by h squared. At home, please also try. Actually, maybe we'll also try central. Getting recorded, so hopefully this rush is not affecting you. So you see that there is a small difference between the forward and backward difference. It is about 500 parts over 70,000. And you tell me how much percentage is that? That's 500 divided by around 71,000. So it's a small difference between the two differencing techniques. Okay. And if you do central differencing, where is the formula for central differencing? I have this. I'll just make one point and let you go, which is that if you see the formula for the central differencing, pay attention here, please. Take a pause. I'm going to post this file anyway. The formula for central differencing involves not 3 but 4 neighbors. I plus 2, I plus 1, I minus 1, I minus 2. So if you count, it's 4 neighbors, 2 on either side. We were able to involve only 3 there, but if you do the derivation, you will find out it's not possible to get a second order derivative approximation using only 3 neighbors. It's either 2 or 4. For some of the quirks that come up in the derivation, you can only involve 2, 4, 6, 8 neighbors and not odd number of neighbors. Okay, but the implementation should be straightforward. Punch in the formula and get the value, and we'll compare it. Okay.
I have no idea what it is. Yeah, it's a complicated zero. That's a bit right now.
I was thinking about it. I didn't hear you.
One second, one second.
Okay.
One second.
I gotta go.